Hello, everyone. I hope you are staying healthy and are having a good week. So, as promised, we are moving right along into our next chapter, which is chapter 11, chi-square. So, chapter 11, chi-square. Making sure that everything looks okay. So the thing about chi-square is that it's going to be kind of different from the things that we've been doing up to this point. So up to this point, our hypothesis testing has pertained to means. Okay, and we know that you can only calculate a mean if your data are collected on the interval or ratio level, right? That's the only way that you can, sensibly calculate a mean. But we know that not all research situations are going to involve data that were gathered at the interval or ratio level, right? Sometimes we might be dealing with information that was gathered at the nominal level, right? So things that are what we call categorical, if we remember, categorical variables, right? And oftentimes we call categorical variables because they pertain to variables that involve simple categories. So something like a response to a question being yes, no, or undecided. Okay, that's an example of a categorical variable. Or if you ask somebody to indicate whether they, agree or disagree with a statement. Or like, and this is a perfect example for right now, if you ask someone to identify their political affiliation, and so you divide them like Republican, Democrat, Independent, right? Or male, female, right? Black, white, other, right? Hispanic, non-Hispanic, right? All of these are examples of categorical variables because they are representing these nominal level measures, and they are all categories. So you can't calculate a mean on that. It would it would not make sense. So when we find ourselves in a situation, a hypothesis testing situation, where we have two categorical variables, that's where we use the chi-square. Okay, so there are two different types of chi-square tests. There's the chi-square test of independence and the chi-square test for goodness of fit. Okay, and both are going to be appropriate for situations involving categorical data. We're first going to talk about the chi-square test of independence. Basically, the chi-square test of independence allows us to determine if two variables are associated in some way, right? Are these variables associated, or are they independent, right? Hence the name. Okay. Sorry, I'm still using this janky notepad that I bought myself from Walmart. Okay, so for example, we could use the chi-square test of independence to answer the following questions. Is a person's political affiliation associated with their attitudes on a certain issue? Usually, yes. Is gender associated with college major? Is geographic location associated with attitudes on a certain issue, right? So on and so forth. Sorry, my handwriting is looking wild today. Okay, and so as we talk more about the chi-square test of independence, we're going to kind of go beyond the specific test application. We're going to learn, a lot about how statisticians look at the association between variables in general. Okay, and as always, we're going to start with the logic behind the test. Okay. So, whenever we kind of gather information that we're going to use for the chi-square test, our results are always going to be presented in what we call a contingency table, which I'll show you in a minute. A contingency table basically just reveals to us the various possibilities or contingencies in the comparison of the variables. Okay, so if we look at table 11-1, we can see two different contingency tables. Okay, so we see a situation whereby 180 residents are asked to tell us their political party affiliation, okay, Republican, Democrat, or Independent, and their view of, this is an example, their view of the downtown redevelopment proposal. So for, against, or undecided, we can see. Okay, so if we look at pattern A, we see that there are basically no relationships or no associations between political party affiliation and the view of the redevelopment proposal. How can we tell this? Well, if we look, we can see that the same amount of Republicans, Democrats, and Independents feel the same way about the redevelopment proposal. The values in each of these little boxes are called cells. Each of the values in the cells is equal. They're equally distributed. So if that's the case, it appears that there's no relationship between political affiliation and attitudes on the redevelopment proposal. Whereas if we look at pattern B, we can see that there does appear to be a relationship between political affiliation and the redevelopment proposal attitudes, right? So we see that in pattern B contingency table, more Republicans are for the redevelopment, more Democrats are against, and more Independents are undecided. So we see kind of a complete opposite kind of situation. Looking at the contingency tables, right? Whether it's a contingency table that kind of demonstrates that there's no relationship between the variables, no association, and whether or not there's a contingency table that kind of shows that there is a relationship, right? So, you know, that actually was kind of like a bit extreme. It's really often not going to be the case that you find something that looks that perfect, but, you know, that's kind of just for the purpose of demonstration, right? And so, you know, we're kind of thinking about whether or not there's an association between the two variables. Now, what we are asking in that example, when we looked at those contingency tables, basically is, are these variables related? Are these variables associated with one another? Or are they independent, right? Are they independent of one another? And of course, if we're saying that there's an association between the variables, we're basically saying that they're tied together in some way, right? Like there's an element of predictability in the relationship. You tell me someone's political party, I'll tell you whether or not, you know, they support the proposal. Something to keep in mind. At this juncture, we don't know why, okay? We're not explaining why someone's political affiliation might lead them to support or not support a proposal. All we're looking at is whether or not there's a relationship, okay? So all we're looking at is whether or not two variables are associated in some way. So we're not looking at why. We're looking at, you know, kind of, are these variables related or are they not? Okay, so if we think back to our hypothesis testing, we always recall that we start with our null hypothesis. So in the case of chi-square, the null hypothesis is written verbally instead of symbolically. So that's kind of nice. So let's say that we are looking at, we're looking at an example where we want to see, I'm just going to put it right here. Is there an association between two variables? Okay, type of community. So like urban, suburban, and rural. And, okay, I'm going to mark this out. That was a bad move on my part. And intention to vote. So super timely. So yes, no, or undecided. Okay, so if we recall back to thinking about null hypothesis, we always remember that the null hypothesis is a statement, remember, of equality or no difference or no relationship. Ding, ding, ding. That's what we're going to be looking at in this example for chi-square. So our null hypothesis is going to state, literally with words, there is no association between type of community and intention to vote, right? It's our statement of no relationship or no association. So when we use the chi-square test of independence, we're testing the null hypothesis by examining the results that we get from our sample data. Obviously, we're still going to be in that situation where we're trying to determine whether or not what we gather in the sample is representative of the population, right? And so what we are looking at is we're going to look at the pattern in the contingency table, or our observed data, and we are going to compare it to what we would expect to find. So, we are not going to deal with the formula quite yet. We are going to look at the data. So let's say that we have gathered information from a sample of 98 registered voters, okay? And we create this contingency table that shows their type of community and their and their intention to vote. Oh Lord. I've got nail polish up on my desk. I'm a mess. This guy wants to keep falling over. Okay. So type of community, and I'm not going to try to get fancy with my writing because that's what messed me up. Voter intention. Oh, yeah. Clearly I don't write like this often. Okay. So let's say that we have the following. So urban, suburban, rural, total. Okay. And then we have intent to vote. Yes. No. Undecided. Undecided. Total. Okay. So let's say we find the following. Okay, so we found the following. We see that what we have written right here, the information that we got from the sample, are the observed frequencies, We have a total sample size of 98. These are our rows. These are our columns, and these are our total, our marginal totals, okay? This is what we call a 3x3 contingency table because there's 3 rows and 3 columns. We don't include the totals in that. So we have a 3x3 contingency table. It has a total of 9 cells, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. So it has 9 cells. Okay? And we see in each of these cells the observed frequency. Okay? We see that 8 respondents reported that they are urban residents who intend to vote. right? 17 are suburban residents that intend to vote. 7 are rural residents that intend to vote, okay? And so on and so forth. So we have these 9 observed frequencies. Now what we need to find are our expected frequencies, okay? The expected frequency for each cell is just a statement of the frequency that we would expect to find given the distribution and the total number of cases. So the way we calculate the expected frequency of each cell, so the expected frequency of each cell is equal to the row total times the column total divided by n, okay? Row total times column total divided by n. So the way you symbolize expected frequency is actually just F sub E, expected frequency. And so we can go through and we can calculate the expected frequency for each of our cells. Okay, so let's start with the urban yes, okay? Row total, 32, times column total, 33, divided by n, 98, okay? So 32 times 33 divided by 8 gives us an expected frequency of 10.78. So the way I like to depict it is I like to put my expected frequency right next to my observed frequency, but in parentheses, 10.78. Okay? Next, we can do suburban, yes. So that's going to be, again, 32 times 32, right? We're in a different column now, divided by 98. That's going to give us an expected frequency of 10.45. The dogs are outside playing wild and barking. It's a beautiful day. And we're in here doing statistics. That's how much I love you guys. I'm not enjoying this beautiful day outside. We are doing statistics, which is pretty beautiful in and of itself. Okay, next, rural yes, 32 times our new column, 33, divided by 98 gives us 10.78. Beautiful. Okay, next, let's move on to urban no. Okay, row total, 29, times column total, 33, divided by 98. That gives us a value of 9.77. 9.77. Okay, suburban no, 29 times 32 divided by 98 gives us 9.47. 9.47. Next, rural no, 29 times 33 divided by 98 gives us 9.77. Perfect. Let me open this blinds to get a little more light on this. Okay. Next, moving down to the last row, we'll do urban undecided, 19. Oops, wrong, I got distracted. Row total, 37 times column total, 33, divided by 98 gives us 12.46. Next, 37 times 32 divided by 98 gives us 12.08. Lastly, rural undecided, 37 times 33 divided by 98 gives us 12.46. Yay! Okay, so look, we see in this contingency table, we've got all of our observed frequencies and all of our expected frequencies. Okay, so now that we have our observed frequencies and our expected frequencies, we're in a position to actually go into the calculation of our chi-square. So the formula for chi-square is as follows. So the symbol for chi-square is the Greek letter chi. It's actually technically pronounced chi, but I'm not going to make you do that. So it kind of looks like one of my professors when I was actually in your position when I was an undergraduate taking statistics about 20 years ago. My professor said that the chi looks like a drunk X, and that always makes me laugh. So the chi-square formula is as follows. So chi-square is equal to the sum of FO, observed frequency, minus FE squared divided by FE. Okay? So it looks a little complicated, but keep in mind that there's really only two components, the observed frequency and the expected frequency. So admittedly, it does take a minute, but it's not that bad. So if we refer to our, I'm going to rip this out. If we refer to our can you see that? See that? If we refer to our paper, we basically will just go through and work this out. Okay. So chi-square is equal to, let's start with urban yes. Okay? FO, 8 minus FE, 10.78 squared divided by 10.78. We can go through and do the calculations after. Okay? Plus, you see that? Okay. Next, 17 minus 10.45 squared divided by 10.45 plus 7 minus 10.78 squared divided by 10.78. Perfect. Next, 6 minus 9.77 squared divided by 9.77. Okay, next, 8 minus 9.47 squared divided by 9.47. Okay, next, plus 15 minus 9.77 squared divided by 9.77. Perfect. Next, plus 19 minus 12.46 squared divided by 12.46 plus 7 minus 12.08 squared divided by 12.08 plus, last one, 11 minus 12.46 squared divided by 12.46. Now, if we go through and work this out, 8 minus 10.78 squared gives us 7.73 divided by 10.78 gives us 0.72 plus 17 minus 10.45 squared gives us 42.90 divided by 10.45, which gives us 4.11. Okay, next, 7 minus 10.78 squared gives us 14.29 divided by 10.78 gives us 1.33. Okay, next, 6 minus 9.77 squared gives us 14.21 divided by 9.77 gives us 1.45. Okay, next, 8 minus 9.47 squared gives us 2.16 divided by 9.47 gives us 0.23. Next, 15 minus 9.77 squared gives us 27.35 divided by 9.77 gives us 2.80. I'm going to move this away. I'm good. Okay. Next, 19 minus 12.46 squared gives us 42.77 divided by 12.46. That gives us 3.43. Okay, next, 7 minus 12.08 squared gives us 25.81 divided by 12.08. That gives us 2.14. And lastly, 11 minus 12.46 squared gives us 2.13 divided by 12.46 gives us 0.17. Now we got to add all of those up to get our chi-square calculated. And when we add those up, we get a chi-square calculated value of 16.38. Now, as before, we are in a situation whereby we must compare our calculated value to a critical value in order to determine whether or not we can reject the null hypothesis. Okay, so we are going to look at Appendix H. And as before, we are going to find the intersection of our level of significance. Let's say that we had set this at 0.05, right, our standard. So let's say that we've set that level of significance at 0.05. And now we have to determine our degrees of freedom. So for the chi-square test of independence, the degrees of freedom is determined by taking the number of rows in the table minus 1 and multiplying that by the number of columns in the table minus 1. So if we have a 3 by 3 contingency table, which we already knew we did, our degrees of freedom are equal to 3 minus 1 times 3 minus 1, or 2 times 2, or 4. So our degrees of freedom are equal to 4. Now, as before, we consult with the appendix. Okay, let me zoom. Okay, so if we're working at a 0.05 level of significance and our degrees of freedom are 4, we see that our critical value is 9.488. Okay, so our chi-square critical is equal to 9.488. Let me zoom out. Okay, so just as before, we're going to compare our calculated value to our critical value. Our calculated value is greater than our critical value. And as we know, when we have a calculated value that is greater than our critical value, we can reject the null hypothesis, right? We can reject the null hypothesis with the knowledge that 5% of the time we've committed a type 1 error, right? So what are we basically saying? We're saying that there is a relationship between where people live or type of community and intention to vote, right? There is a relationship or an association. Okay, so that's what you get for the chi-square test of independence. I will record the chi-square goodness of fit test separately. Okay.